Hey guys, welcome to another Mr. Fourth Dimension video. This one I'm just going to do a one-off video. I want to talk about rounding because I was working on a project recently and it occurred to me that it's just something I know enough about to make a cool little video about. So we're going to make a rounding.cpp real quick. Let's see, today is 2/16/2015. Let's see. Alright, so let's get a little test system set up here. This is going to be a pretty simple situation. So what we're going to mess with is rounding the floating points, or in my meta file system, the what should I call it? The reals, right? I can't code, I can't like move around in my file system and get stuff set up while I'm thinking too well. But I'm going to pull up my meta file from GeoProject and I'm going to just copy it in directly and throw it at the top. Now, I do believe the meta file has rounding in it, yeah. So I'm going to take those out because I'm going to code those on this video. But the rest of this, well, actually I don't need any of this. Let's just keep everything after this point. Well, yeah, we'll get rid of all of this because we don't really need that for what I'm going to do. So there's our little in-place meta. Now, let's set up the test. I just put that meta in there so that I can do the real 32 the way I'm used to. So we're going to take these floats and we'll make, let's do a for loop, right? So we'll do a for loop on a float, which is kind of weird, but it'll start at 0. We'll say while it's still less than 8, do a plus equals, like, something weird. I think I have a pi up there, don't I? No, I don't. I'll do like a 1/0. Right, that's kind of weird. Well, it's 2. Yeah, we'll do that. That's fine. I want it to be rather irregular, the results that it creates. That should do it. Okay. Now, what we want to do is for each one, we'll make a rounded version. And for now, we'll just do it by directly casting. And if we were about this being an I32, just think of that as an int and that as a float, right? So we're just doing a normal integer cast. Then we'll print it. A rounded, right? So that should give us an idea of what kind of rounding we're getting for this. And I just realized we're probably going to want to start at like negative 8 here so that we can get negative numbers in there too, because they round differently and that's important. Alright, so gave us a nice bit of output. We can see negative 8 rounded to negative 8, so it, like, if you're on the boundary it works. And then a little bit smaller, or a little bit bigger I guess you could say, a little bit less negative, it went to negative 7. So if you're on whatever number you're on, it sort of goes down to negative 7 no matter what the decimal part is, as you can see. And then the really crazy part about rounding is that it flips, so it's not just rounding up, but when you get to the positive section it starts rounding down. So like 0.9 goes to 0 and negative 0.9 also goes to 0. So it's actually what you call truncation. It's just looking at the integer part and it's ignoring the decimal part of whatever number you have. So that's how the built-in rounding works, which is good for a lot of purposes, but sometimes you just want it to always ceiling or to always floor. And what I mean by that is ceiling is what it's doing in this positive range, it's always going up, and floor is what it's doing here, it's always rounding. Actually, no, I got that backwards. It's always flooring here, going from 0.9 all the way down to 0, and it's always going ceiling here, going negative 0.9 all the way up to 0. What if I wanted to do ceiling on the positive range too. Let's write a ceiling function. So I like to make these inline. I have them return an I32 because I'm normally converting to I32 anyway, and that just saves me having to do a cast. Because if I return the rounded version of a real 32, then I still have to cast it to an int, which isn't going to change its value. It's just extra typing I have to do to get rid of warning. So there you go. That should be convincing enough. And we'll write ceiling here. And I like to do x is the thing I'm going to round. So how am I going to make sure it always goes up? Well, the simple logic is if x is less than 0, you just return the straight rounded version. And otherwise, what you have to do is you have to say, alright, return you know, the rounded version plus 1, right? That seems like it should work, because this is going to round down when we're in the positive range, so if we add 1, it fixes, right? I think it'll look like it's working. This is always the problem with rounding, is you gotta make sure you test what are actually boundary cases. So you see, I picked a number, the 0.1037, that never actually lands this on an integer so that we can see what happens. But what happens if we put in a 1 there? So let's test that, and the way we can switch to testing that is we'll pick something more regular. 125. Alright, so now, when it's trying to, oh, that's the other thing I gotta do. Actually, whatever I just said was a lie. I was going too fast. I've also got to switch this to seal. There we go. So now we can see the problem. This 8 is rounding up to 9 because 8 itself truncates down to 8, but it truncates back to itself as 8, and then we added 1. So all of these numbers are actually rounding up when they shouldn't. 6 should be 6, 7 should be 7, right? And rounding, if you're on a boundary, you don't want to change your value. But what we're doing here works everywhere but on those boundaries, right? So we've got a problem. Now one thing we could do is we could fix 0 by saying this, but that doesn't matter too much, right? We still got to fix this. So what we really want to say is if the rounded version is equal to this, then just return itself. Otherwise, return this. Right, so that's starting to get a little nasty, but let's see how if it at least works. The -8 is correct. All of these are rounding up to the ceiling of -7. These are all rounding up to -6, -5, and so on. Looks pretty much correct. Then 0 is 0, and 0.125 is 1, 1 is 1, 8 is 8. So it looks like it worked. But we kind of want to, we don't really want to have this. The problem with this is even if you're on, well, the reason I don't like to do a ceiling like this is I just like to be able to have things like seal work without ifs. Having branches is annoying. Now you might say like you don't need to optimize this because you know it's premature. Well, my argument is it's premature if we're writing a big old program that's complicated to optimize something that makes our life harder. But if we can optimize this now, then it's always just going to be optimized and we can have it forever. So we're going to optimize this. This is even if my argument, even if you didn't accept it, let's just say that my requirement is the fastest seal possible. Well, this is not the fastest seal possible. It's also the fact that if you try to use this on a GPU, if you're programming GPU, this just won't work. You need a closed form solution. So to do that, one thing you might think about doing is using that, you know, this trick. But that is a lie, right? In my experience, when I time this is often the same thing. It actually causes a branch. I haven't looked at the machine code, which I probably should do before I actually totally claim it, but at least in terms of speed, that doesn't really help much more. So I assume it's still branching on my computer when I do that. But there's still a solution, not to worry. We just have to use, we have to be a little more clever. Now the nice thing is, these things here, this, if here, and this if here, actually I should leave it there as well. So we have the original code. Now we're going to try to transform that code that works, it's simple to write, we're going to transform it into the closed form solution. Now the trick is that these two expressions are either 1 or 0. This is a 1 if it's true and a 0 if it's false, and this is a 1 if it's true or a 0 if it's false. So we can use that and then just do math with 1s and 0s. Multiplying by a 1 and a 0 is a good way to simulate an if, right, in a closed form expression. So let's get to it. First of all, let's just say we want to return the cast of x, right? But we really only want to, we also want to say we were going to add 1, but we don't always add 1. So we want to multiply that by 0 if this is true. So we want to multiply that by x being greater than 0. So if x is greater than 0, this will become a 1, and then this won't get turned into a 0 in the multiplication. But there's another thing we can do. We can multiply the whole thing this again, because we also want it to become a 0. Technically this should say I32x, right? Do the cast. We also want to say, look, only do this plus 1 if this part is not true. So it's like I32x does not equal x. So if these two guys are not equal to each other, this will be a 1. If x is positive, this will be a 1. Then this whole thing will be a 1. Otherwise, it's going to be a 0. One of those two or both of them is going to make this multiply out to 0. And then we have you know, the actual addition. So we do the round the normal way, and we get this plus 1 when we need it. So that looks correct. Let's test it. So that's better, because it's still working, and now we've got the ifs out. But let's see if we can take out time. So I'm not sure about this. This is a new experiment, and we're going to see if I can get it done. My idea is this is always a 1 or a 0. This is always a 1 or a 0. This is always a 1. We could just bit and these together, and that is probably faster than multiplying them in this case. Well, not that it's in this case it's faster, it's just it might be correct in this case. So that's not quite right. But I think that's just a matter of parentheses. Let's put parentheses here, because I think it's doing a bit and on the whole expression after the 1, after the plus 1. See, that's right. That works. What I was going to say is, if I was writing a language, one thing I would do is I would have it pay attention to white space, like the distance I put between these pluses. If I put things nearer to each other, they should bind first, even if the language doesn't say that. I mean, maybe that's not a good idea, but I'd at least try it because it seems interesting. It's a quicker way to group things together than wrapping parentheses around stuff, certainly. So the same concept now we can apply to how we do a floor function. Let's we could try to skip to it by like manipulating that until we got the right answer, but I prefer to just do the easy way first. So if x is well, first of all, let's see what kind of changes we even need to make I32 into a floor, right? Let me run this again. Okay, so to make this into a floor, these are all right, this is all right, so all the positive stuff is right. It's the negatives, right. So the negatives are the part that don't work on floor, because this should all be rounding to -1, and it's not. So to make a floor function, we're going to say, take in a real, and then we're going to cast it, but that's not always going to work. So we're only going to do that if x is greater than 0, right? Because that's when it works. It could be equal to as well. Alternatively, return this and then subtract 1, right? We want a -1 because these are supposed to go lower than they do. So if x is negative 0.5, say, it'll round to a 0 with this, and then it'll become a -1. And then there's that problem where if we do this, and I put in a -1, this becomes a -1, and then we subtract 1 and it's -2. So we still have to do if the truncated version does equal x, then just return the x directly. Otherwise, do this, right? So now if we switch to flooring this, so those are all -1s, those are -2s, and it looks like we're flooring correctly. Now we want to do the same thing as before. We're going to transform that into the same idea. So one thing we found by doing this guess the easy way for us is that it was subtracting. If I was just trying to manipulate, I probably would have done an addition still, which would have been wrong. Another thing is that this is a flipped sign from what we had last time. I've deleted it now, but this is flipped sign, so it's actually probably going to be the flip of this is my guess. And we can skip to this since we know that this will work. But basically that is, if x is less than 0, it's negative, and so this should be a 1. If I made this say, basically what happens here is this subtract minus 1 only happens if this is true and this is true, right? We're saying subtract 1 if this is true, if this is true and if this is true. So if x is less than 0, subtract 1, and x has to be not equal to its truncated self. So, yep, those are still flooring correctly. So that's basically the way I set up a ceiling and a floor. If you want to turn this into a round now, that'll just round any, like using the typical rule where a 0.5 goes up and a 0.4 goes down. Then what you're doing there is you're saying, well, you're basically doing what we're doing now. It's a ceiling or it's a floor. We'll have to figure that out. But you're just doing it on a 0.5 different boundary than what we're doing here. Because here we're rounding to a nearest integer. We're not to a nearest integer. We're rounding upwards or downwards, and we're trying to do a nearest integer. But what we could say is just shift everything over by 0.5, then do the round, then shift it back. And the reason that'll work is because then we're shifting the boundaries of where we do the rounding. If that's not clear, it'll become clear in a second. So say I want to round 0.5. What should that become? It should become a 1. So what I could do is I could say ceiling that, but if I say ceiling on a 0.4, that'll be wrong. So the trick is that we're going to take the 0.5 and we're going to add 0.5 to it, and then we're going to floor it. But a 0.5 plus a 0.5 will give us a 1. Whereas a 0.5 plus a 0.4, which is still a 0.9, floored goes back to 0. Similarly, if I look at negative 0.5, if I add a 0.5 to that, I get 0, so when I floor it, I get 0. And if I take a negative 0.4, for example, and I add 0.5 to that, I get a 0.1. When I floor it, I get 0. If I take a negative 0.6, when I add the 0.5, that goes to negative 0.1, so it'll still floor back to negative 1, and so on. So in other words, the answer is we want to floor x plus 0.5. Right? So let's try round. And now 7.5 rounds up, 7.37 rounds down, 6.5 rounds up, and so on. Let's check the boundary case. 0, yes, negative 0.5. So the negatives are also working the same way, right? 6.5 rounds up to 6, but it's negative 6.625 rounds down to negative 7. Negative 7.5 rounds up to negative 7, so on. If you wanted to, you could also do the other one, which would be to do ceiling here and a negative 0.5 here. And what that does is it says take a 0.5. So this is like rounding with 0.5 being inclusive, and you could also do round nearest 0.5 being exclusive. So it will round down is probably the better term for that. I'm thinking like exclude it from the round up selection for rounding up. So exclude 0.5 or include it. But anyway, that's a little, what is this? Almost 19 minutes on rounding. Hope it was interesting. Hope you can find other ways to apply this code transformation method where you write the easy thing and then you figure out how to transform it into a cool thing. See you guys later.